Hi everyone and welcome to this episode of Keipert Labs. In today's video we're going to be discussing galvanic or voltaic cells in the context of thinking about redox reactions. So we're going to think about the connection between redox reactions and electricity. We're going to go through the basic design features of a galvanic cell and think about how galvanic cells are set up to generate electricity. We're going to introduce some key vocabulary terms, introduce what we mean by half cells, labels like anode and cathode, and the role of what we call the salt bridge in a galvanic cell, and as well as some different types of galvanic cells. So a fair bit to discuss, so let's get into it as quickly as we can. Okay, so redox reactions and electricity. So we've looked at this idea that redox reactions involve transferring electrons from one substance to another. We can harness this as a way to generate electrical energy. So in order to do that, we need to conduct a redox reaction in a particular way. You've got to set it up in a particular arrangement called a galvanic or voltaic cell, which channels electron flow in a particular direction to harness electrical energy. So we can get that electron flow to travel through an external circuit and do something useful with it. So here we have the basic design of what we call a galvanic cell. Okay, so we have two kind of separate containers or two separate beakers. Now this is the basis of chemical batteries like your AA batteries or your car batteries and things like that. They're all kind of design variations on this. But so we have two separate containers. Okay, so what we have, you can see we've got a piece of copper metal and some silver wire connected up, flowing via a voltmeter in this diagram. We have what's called a salt bridge that connects the two beakers over here, and we have solutions in each beaker. We have a copper 2+ solution on the copper side and a silver nitrate solution on the silver side. So some particular things that we need to do that work with this, so that we've got two separate half reactions occurring in separate locations. Okay, we have two distinctly different beakers here where we get these half reactions occurring. We need to have electrodes that allow connection to the electrical circuit. They can be pieces of metal, or perhaps it could be carbon, or in the form of graphite, or something else like that. It all kind of depends on exactly what's on what side. You need some metal wire or a way for actually connecting the two, whether a voltmeter is here or not. This is only just for measurement, not to make the circuit work otherwise. And we also need the salt bridge. Okay, so there's some key design features that we need in any galvanic cell. Okay, so if we took a galvanic cell that was set up like this, and there would be some things that we would notice over time. Now, I realize this is a diagram, not a photo, but I can't work miracles. Okay, but so what we would see, the copper in this particular situation, mind you, the copper electrode, the piece of metal, would be partially dissolved or corroded. Okay, so it would have slightly eaten away. Over on the silver side, we would have had metallic silver depositing in the form of crystals on the surface of the wire. That the concentration of the silver ions in this side would decrease. Now they're colorless, so we wouldn't notice that, but we could measure it or quantify it. Whereas the concentration of copper 2+ over on this side would increase. So it would become a stronger blue color over time. Okay, and so we can to actually explain how this works, we can try and make sense of what's actually making this happen. So in this particular scenario, the electrons, so chemical change occurred with an electron transfer process, because the electrons flowed out of the copper strip up into the external circuit, then down into the silver wire. So even though they weren't physically touching each other, the electron transfer could still happen. So on the strip of the copper, we had copper metal becoming copper 2+. So it was oxidizing or losing 2 electrons to make this change. At the silver electrode, silver ions were reacting with an electron to form silver metal. Okay, so if we combine these two half equations together, like we've been learning, then what we get is this process. Okay, so where we looked at the fact that all the electrons need to cancel out, so we need to multiply everything in this reaction by 2 to form our overall equation. But if we look at this, we took a chemical reaction, a chemical process, and we generated electrical energy as a result. Okay, there's no moving parts otherwise, but purely chemical change allowed electricity to form. Okay, so this is the basis of the original batteries from Galvani and Volta in the 1800s. So some of the vocab terms that we need to be familiar with: a galvanic or voltaic cell, or their alternate names. So, which is the device in which we're using a chemical reaction in such a way that we generate electricity. So it might happen in a car battery or a AA battery or inside your phone battery. Okay, the electrode is the conductor of the cell, which then connects to the external circuit. So like the metal strips or, some conductive material. The electrolyte is the substance in which conducts electricity when in solution or when molten, so when melted at a high temperature. Okay, so our copper nitrate and silver nitrate solutions were electrolytes in this case. They allowed electricity to flow. And a battery, chemically speaking, is when we take several cells and we connect them together in a common outside casing. Okay, so cell is kind of, chemically speaking, the name for the one of them, and a battery is a series of them. Okay, so a 9-volt battery or a car battery contains several cells connected together in series. Okay, so if we come back to our original diagram, now what we do is we can actually consider each, because we've got two halves here, we can actually consider each one separately. So each one is actually undergoing its own half reaction. So we call it a half cell. So altogether it is a complete cell, but each side is half of that cell. So it consists of an electrode plus its solution. So copper metal plus the copper 2 plus solution. Silver metal plus the silver 1 plus solution. So they are the different half cells in this particular galvanic cell that we're connecting. Okay, so depending on how we're setting it up, that each half cell might be different. We might take out the silver and swap it for zinc, or we might take out the copper and swap it for iron. Okay, so the idea is that we can still have a galvanic cell if we swap out one half cell for something else, but you need to have two for it to work. You need to have electrons going from one thing to something else. So in this example, we've got a copper 2 plus and copper half cell. We've got a silver plus and Ag plus and Ag half cell. So on each of those sides of the diagram. Now it doesn't matter which way is connected, left or right. That's not really important, but just recognizing that we have two halves connected to make the whole cell. Now in a galvanic cell, we recognize that yes, we have two halves, but we want to label each half in terms of what changing process, excuse me, I'll just come a bit closer, what changing process is occurring. So we use two labels we call anode and cathode. So the anode in a galvanic cell is the place where oxidation is occurring, okay, and the cathode is where reduction is occurring. And electrons always flow in a galvanic cell from anode to cathode. Okay, now this is a bit of a bugbear between chemists and physicists and going back hundreds of years of starting terminology and all this sort of malarkey. Unfortunately, I can't help you with all of that. To just say this is the terminology that we use as chemists, and so identifying that in this situation, because we've already seen that copper is oxidizing, that we would label it the anode. We've already seen that silver is reducing, so we'd label it the cathode. Okay, we need to know which process is happening in which in order to be able to label them. You can't just decide, oh, the one on the left's the anode. Okay, but once we have identified that, then we can be confident in using those labels. But the question then becomes, how do you remember which process is happening at which? I've got a nice little tip for you. Okay, two kind of ways. One, whichever one is more memorable for you. So we can say anode equals oxidation, so anox. Okay, so here we have a picture of a very friendly ox, a musk ox, I think this one is technically, but who cares? Okay, so anode oxidation or anox, or cathode is reduction, red cat. Okay, I like this picture. I think you might be able to remember that well. So red cat is, for me, easier to remember. Reduction at the cathode. You've only got two choices, so if you can remember one, you can automatically remember the other as well. Okay, but you do need to be able to remember it, just like you need to know what oxidation and reduction are in terms of loss and gain of electrons. Okay, there's a few things within this concept where, in this topic, that you've got kind of two processes to remember. Okay, so in our galvanic cell, we introduced the salt bridge, and we said that it was really important. But now I'm going to talk to you about why it's important, what it actually does. So when we have these two half cells connected in a galvanic cell, we're going to get a change in electrical charge occurring at each side. Okay, so the anode half cell, because it's oxidation, it's losing electrons, therefore it's becoming more positively charged over time. The cathode half cell is doing the opposite, gaining electrons and becoming more negatively charged. The problem is that when we end up with this significant difference in charge, that then it basically halts the flow of electrons. Okay, because the electrons are not going to head towards the one where they're going to be gained if they're being repelled by its negative charge. So the presence of the salt bridge helps to maintain what we call the electrical neutrality of the cell. So it allows current to flow by helping to even out the charge in the sides of each side of the galvanic cell. So the ions that are dissolved in that salt bridge will be able to physically migrate or move in order to balance out the charge. The positive ions or cations flow towards the cathode. The negative ions or anions flow towards the anode. This is actually where these names of cations and anions stems from, the direction in which they're going to flow in a galvanic cell. So cations towards the cathode, anions towards the anode. Now, if there's no salt bridge, there will be no voltage. There will be no flow of electrical energy because of this buildup of charge. Okay, so it's really important that we have that salt bridge there, and we also dissolve it in a salt that is not going to precipitate with any of the substances in the reaction. So things like sodium chloride or potassium or even nitrates and sodium or potassium salts are the best by far. So sodium or potassium nitrate will be a hands down winner for any salt bridge that you construct in chemistry. Okay, so then we have a few, I want to introduce you to a few of the types of galvanic cells that we come across. So we have single-use, non-rechargeable batteries. So your average AA dry cell battery. Alkaline kind of batteries, alkaline cells. Silver oxide or button cell batteries like you might have in a watch. And then a lithium cell, a version of which is present inside your mobile phone, for example. And then we also have rechargeable batteries, so that it can be reused, can be topped up. We have the lead acid cell, which is the basis of your car battery, or your nickel cadmium cell, or your NiCad kind of battery. And so then we've also got other like lithium metal hydride and things batteries, but we don't talk about those within our context. And the two ones with the asterisks are not actually needed for the HSC course, but they are relevant to those kind of sections of what we're talking about. Okay, and there are a couple of other types of galvanic cells. We have a fuel cell, which is where we're recharging not by putting more electricity into it, but by adding more of a chemical fuel into it. So a hydrogen fuel cell, which powers certain types of cars these days. We also have the vanadium redox cell. And then we have a liquid junction photovoltaic device, for example, called a Gratzel cell, to be familiar with. So where we're combining your typical photovoltaic cell, like in a solar panel, with a galvanic cell to help generate electricity from sunlight in a particular way. Okay, so we looked at the connection between redox reactions and electricity. We went through the basic design features of a galvanic cell and how that allows electrical energy to flow. We introduced some key vocabulary terms. We talked about the fact that galvanic cells are made up of two half cells with each half reaction occurring. We can label those two halves as anode and cathode based on the process that's occurring at each one, and the importance of the salt bridge in maintaining the success of a galvanic cell, as well as the different types of galvanic cells that we commonly encounter. Thanks very much for watching. Bye for now.